Good afternoon, ladies and gentlemen. My name is Michal Šprlák and I come from the University of West Bohemia in Pilsen. Together with Činchan Han, Martin Pitoňák and Pavel Novák, we worked on the evaluation of external spherical harmonic series inside the minimum brilliance sphere. I start with a short introduction. External spherical harmonic expansions are a popular mathematical tool for computing gravitational field quantities. The convergence domain of the series is the space above the minimum brilliance sphere. Besides, we commonly use these series inside the bounding surface. Justification of this analytical downward continuation procedure has been debated for decades, but conclusions may be indefinite and even contradictory. In this talk, we literally test the analytical downward continuation, and we do so for the gravitational field of the Moon inferred by topographic masses. Such field perfectly correlates with the realistic one observed by the Grail satellite in 2012. We analyze two quantities on the sphere of radius 1738 kilometers. Calculations and interpretations of the lunar gravitational field are routinely performed on this surface that is 10.2 kilometers below the minimum brilliance sphere. The first quantity is the radial derivative of the gravitational potential. It can be represented by the blue external spherical harmonic expansion of spherical harmonics y and m. I recall that this series is exact only above the minimum brilliance sphere and is analytically continued downward in our calculations. Alternatively, we can express the radial potential derivative by the red internal expansion. This one is exact inside the minimum brilliance sphere and composes of two terms. We calculated the spherical harmonic coefficients CNM, CNMO, and CNMI up to degree 1800 from a high resolution LOLA topography, assuming a constant crust density. The signal of the red internal expansion decreases with increasing harmonic degree, just as we expect for a physically meaningful quantity. On the other hand, the signal of the blue external expansion increases, that indicates divergence. Let us now look at the maps. These were synthesized between harmonic degrees 150 and 600. Both fields have low amplitudes in Procellarum Craterinae on the near side and in South Pole Aitken Basin on the far side. High amplitudes are visible over the lunar highlands. It seems like both series result in similar gravitational fields over the near side, but the correlation coefficient is lower than 0.5. Conformity of both fields is completely lost on the far side and globally, where the correlation is almost nil. The second quantity is the second radial derivative of the potential. It can be computed by the blue external expansion and analytically continued downward. The internal expansion is exact inside the minimum brilliance sphere. The second potential derivative may be discontinuous, and the internal expansion also contains the third so-called density term, which eventually has to be considered inside the masses. The signal of the blue external expansion again increases, and even faster than for the first derivative. On the other hand, the signal of the internal expansion drops. The black curve shows the signal of the density term and is larger by almost an order of magnitude than the red curve. Thus, the density term clearly dominates the size of the internal expansion. Let us now observe the maps of the second derivatives. The maps of the blue external series at the top and of the internal series without the density term in the middle look alike. On the near side, where the correlation is higher than 0.9. A reasonable similarity is also preserved on the far side and globally. However, the amplitudes of the second derivatives by the blue external expansion are significantly higher, for example, over the lunar far side. Features of the second potential derivatives completely change when adding the density term, as can be seen at the bottom. The correlation coefficients of this map with the one at the top are much smaller and become even negative. I have to stop at the best and go to the conclusions. In this talk, we evaluated external spherical harmonic expansions inside the minimum Brillouin sphere. We demonstrated some serious issues of this series and also that the density term cannot be neglected when calculating the second potential derivatives. Our findings have important implications for the gravitational field modeling in general. For example, we may ask if gravitational fields constrained by Kaula's rule are truly realistic. Finally, to those who are interested in further details, I recommend to read our article that got published in Earth Science Reviews. That is all from my side, and I would like to thank you for your attention.